Cool.
Hi, everyone. Today we have Benedikt as our speaker. He's a fifth-year PhD from Stanford University. He's going to talk about his work, proof carrying data without succinct arguments. Let's welcome him.
Hello, everyone. I'll talk about our new work on sort of recursive proofs and how you can construct them without succinct arguments. And this just got accepted to crypto this summer, so we're kind of excited. I don't know, actually, it's probably not CMU securities. I mean, I just called it that. But yeah, you can find the paper online, and this is joint work with some folks at Berkeley, and I guess Nick is now at BU. And yeah, if you have any questions throughout, then I'm happy to dive into sort of as much detail as we want to. We're a small group here, so let's try to make this interactive. So what is the motivation? So what we want to do and what we achieve in this work is we want to delegate a long computation. So a long sequential kind of computation. So this is a t-step non-deterministic computation. So I have some function and I have some output z0. And I want to show that basically there exists some intermediate values to this computation and some intermediate witnesses, such that sort of applying f over and over again to z0 and these witnesses, I end up with zt. So f of zi comma wi is equal to zi plus 1. And I want to prove that this computation might take a long time. So I want to prove, we were talking about verifiable computation. So I want to prove to some verifier that this computation was done correctly. And the way to do that is I could just throw a SNARK at it. So I could create just a monolithic proof. I encode the function f to the power of t. So f applied t times in a circuit, apply my favorite SNARK technique to it, and I get out a succinct SNARK that is efficiently verifiable. The issues with it are that it typically requires a lot of memory. I have to store the entire computation in memory, or so it's linear in the space needed to evaluate f times the number of steps that it takes. And it also, creates, and sometimes it's even super linear in that, like I need to apply maybe some FFT to it. And this is both theoretically and practically an issue. And then additionally, say I want to extend the computation by one more step. So I want to compute f of zt plus 1. And the problem with that is that now I just have to recompute the entire proof. So I have to do basically work that is now still linear in t plus 1. Even though I'm just adding one additional step in the computation. I could also just give you one proof for the first t steps and then one additional proof for the second step. This works for one step, but the problem is we obviously, if we keep doing this, we lose the succinctness, right? If I keep just adding proofs, then in the end I will have a linear number of proofs. So verifying them, or just the size of these proofs, there's no way that they can be succinct anymore. And option 2 is something called incrementally verifiable computation. And this was proposed way back in 2008 by Valiant. And here the idea is that instead of having one monolithic prover, I'll have a prover that takes as input the computation and say it does one step of the computation and outputs a proof. And then the next prover will take as input, so I have a new prover then after one step of computation, it will take as input Z1 and the old proof, and it will basically update this proof to create a new proof, pi2, and continue on doing that. So, this is called incrementally verifiable computation because I incrementally update this proof. And now the idea is that the size of the proof and the time that PF takes is constant or independent of T. It doesn't matter how many steps I've previously done, the size of the proof should be independent of that. And proof carrying data is basically a generalization of option 2, which says, okay, the same principle of kind of updating these proofs actually doesn't just apply to kind of these lines, so line computation, but to entire graphs of computation. And this can be incredibly useful if, for example, I have multiple provers that each, they prove different statements, and then I want to combine these proofs. Because as you see here, say, you guys see my mouse, right? So as you see here, the PF takes as input witness t minus 1, zt minus 1, and pi t minus 1. But it doesn't even take as input all of the previous witnesses or all of the previous computation results. It doesn't need to know them. This is really, really important. A, because we want this prover to be succinct, but also if we have distributed provers, so if we have, say, multiple provers working together, they can each, compute the proofs on their own, and then, you have some proofs that combine them, and so on and so forth. And no one, like once kind of this computation has been aggregated into a proof, you can forget about what the previous computation steps were. This is again why this approach requires much less memory. And there's a bunch of applications to them. Succinct blockchains, I'll go into that in a second. SNARKs with low space complexity, as we already mentioned, you can construct verifiable delay functions from this. This is useful for Byzantine agreement, and so on and so forth. There's been like one really fun application is, I think, there's like this thing called photos proof or photos snark, which, and I think this is demonstrated in practice, is if I take a picture with a camera, and then I want to do, some Photoshop modifications to it, but only limited amounts. And I want to prove that, basically this is kind of still an original picture with, maybe just like slight, it's okay to rotate it and so on, but it's like not majorly modified. And people have shown how to do this, and this is like, a step-by-step computation where I apply these updates one after another. And people have shown how to do this with proof carrying data. So I said succinct blockchains from IVC. I want to quickly go into how this might work. Well, so say I have a blockchain, not a succinct one. So say Ethereum, this has which has a bunch of blocks and a bunch of transactions. And I think in Ethereum, this is like, we're way over a terabyte at this point. And if a new user wants to join, well, in theory, this new user, might have to download all of the blocks and check all of the transactions that ever happened in this blockchain. So this might be incredibly cumbersome and take a long time and be basically impossible if you want to, say, do it on a mobile device. So usually what people do is, the practical solution is you just trust someone else, but this isn't really in the spirit of blockchains. Ideally, if you want to run a so-called full node, you ideally would verify that every single transaction that has ever happened in this blockchain is correct, and that all of the hashes are correct, and that whatever consensus mechanism is used was correct as well. So one thing that we could do is what we would ideally have is we would have a commitment in each block, and a proof that says that all of the transactions in this block are valid, and the commitment is a commitment to the current state. So you still need to know what the current state is, so which account has how much money, but it's okay to have a commitment to that. And then the succinct blockchain basically just says, I have a proof attached to every block, and this is an incrementally verifiable proof such that it can be updated quickly. And I just download the latest commitment of the block, which commits to the current state. And then I have a proof that basically this commitment is correct with respect to the entire history of the blockchain. So that all of the transactions were correct and all of the hashes were correct and all of the consensus stuff was correct. And yeah, then after that, I should be convinced and that this is, that this blockchain is well formed. And concretely, what Pi4 will say, it's an incrementally verifiable proof. So how do we implement Pi4? Well, Pi4 will say that the previous proof was valid. So, and that all of the new transactions in this block are valid. And the previous block being valid, the previous proof being valid has the same form. The previous proof will say all the transactions in block 3 were valid and the proof before that was valid. And if we continue that to the end, we know that this is, where these proofs are called recursive proofs. It recursively implies that all of the transactions in this blockchain are valid and that the current state commitment that I give to you is actually a valid commitment to the state. And now the new user is happy and only has to download a single commitment and a small proof. And yeah, they reduce these succinct blockchains reduce the synchronization cost, and this has actually been demonstrated both in theory, but now this is also applied and done in practice. So there's a blockchain called Coda, I think, that uses these recursive proofs in practice.
Could I ask a quick question about the trust assumptions here?
Yes.
So if you go back to the naive version of this, right, you said that ideally somewhere you obtain the root, the original root, and then you check that everything after that was done correctly, right? But
can you say that again? I don't think
so even in that naive one where you actually physically check all the transactions and make sure that they're all chained together,
yes,
like there is an initial block that they have to have started from. If I can give you a bogus starting point, and
right,
then no matter what checking you do after that.
Yes. So the starting block is usually that is hard coded. That is we just have some that's hard coded in the protocol. So we assume that everybody there's some out of band consensus basically on what the starting block is.
Yeah. So I guess what I'm wondering is, I mean, if you have an out of band mechanism for that, is an out of band mechanism you can use more often than once, or is there a reason not to use it more often than once?
Yeah, I mean that's a legit question. I mean, I think there's sort of in
it's kind of distasteful,
reality. I mean, is it possible to know what the state of the Bitcoin blockchain was like a year ago? Like probably, yeah. I mean, it will be hard to fool anyone, but I mean, it's I mean, I think it's okay to encode something once in the protocol. I think then basically there's like one thing that can happen, for example, is that there's different like the Bitcoin blockchain, for example, has forked, right? So people actually, there is a real disagreement on what the Bitcoin blockchain is. There's Bitcoin and there's Bitcoin Cash. Some people might say Bitcoin Cash is the real Bitcoin, and then there's Bitcoin Satoshi Vision, and there's a bunch of it, I mean, like there's not real consensus on which one it is. I mean, and so I think, yeah, maybe it's just not that clear, and I think that's hard. But that gets more actually into consensus questions, I would say.
Yeah, I guess. And then what is the connection to once you move to a succinct blockchain? Like, is there a pointer to somewhere baked in the notion of the original root, and we also have to agree on the original root in this case?
Yes. So in all of these blockchains, in any blockchain, you have to have kind of the it's called the Genesis block.
Right.
Is hard baked into the protocol.
Okay, and that would still be baked into your succinct blockchain?
Yeah, that would be basically the proof. Pi1 would basically say, I mean, sometimes the Genesis is literally just a string, like the string might say, it's the hash of, I think like in Bitcoin, it's like the hash of some newspaper headline, people do fun stuff with it, but basically the Pi1 would say like this proof starts with a certain string, that this hard baked magic string, and then all of the transactions in block 1 are correct.
And then I guess part of your recursive proof statement is that I checked that the proof is correct and was pointing to this original block, or that
right. It's like I mean you basically must have. I think you have a in general you have to have a branch here, right? Like there's like the branch for the zero case, the starting case, where you check kind of if I'm block one, or I should really start with block zero. As a computer scientist, but if I'm block zero, then I check that I don't know, this hash is correct, or else I check a previous proof, right? Pi1 cannot check a previous proof because there was no previous proof.
Cool. Okay. I think that clears things up. Thanks.
Yeah.
I have another question. So like, if you use the SNARK and then you use this recursive composition, you can only do it for constant number of steps, right? Because the extractor size will have exponential blow up.
Right. So, I mean, in practice, you can do whatever you want. So theoretically, right, there's a theoretical issue with using the doing IVC for many steps, because as Elaine was saying, the extractor size blows up. The way to get around this is basically to use PCD and build a tree. So I build, instead of having sort of a chain of proofs, I can just have a tree of proofs. And through that, I can limit then the middle nodes in the tree will say that the two child proofs are correct. And through that, I can have a log depth tree, or I can even, if I increase the branching factor, then I can even have a constant depth tree, and that is the way to get around this issue. In practice, people just do a chain, but theoretically, to get around it, either I assume, I mean, there's I can also make a really, really strong assumption on the size of my extractor, like that it's literally just, I think that it's literally just linear, or that it, I don't know, that it just doesn't grow at all, or I can do a tree-based version of. Okay, any more questions? Okay, then moving on. So how do we construct IVC? I've already hinted at this, but so far, the way that we construct IVC is from SNARKs. So SNARK is a succinct non-interactive argument of knowledge, and succinct here in previously, so BCCT 13 constructed IVC from SNARKs. So by succinctness, I mean the size of the proof here, to be precise, but previously we constructed IVC from SNARKs that have succinct and short verification, so constant or polylogarithmic verification. Then later on in 2020, it was shown that it's actually enough as long as the verification is sublinear. Then you can construct recursive IVC. And then last year, or in 2019, end of 2019, there was this paper called Halo, and had some really interesting ideas in it regarding recursive proofs. And we showed then that, we formalized this and showed that their approach is actually enough to construct IVC from a weaker primitive, which is called sublinear accumulation. I'll go into this. So where we can just accumulate proofs, but still we need these SNARKs. We still need a succinct proof, just sort of the requirement on the verification time for the SNARKs. So these are SNARKs with linear verification time, but kind of this accumulation, sublinear accumulation theme. And now, but the question is, do we really need SNARKs? And intuitively, it seems so. But it turns out, right, and there's, in some sense, the answer has to be yes, because from IVC, I can build SNARKs again. So, there seems to be some equivalence here, like SNARKs imply IVC and IVC implies SNARKs. But we can actually show that we can construct IVC from something that is qualitatively weaker, and this enables new construction with new efficiency properties. And here, this is exactly what we do. So
I guess I have another question. Sorry, I'm a little bit confused. So this IVC doesn't require knowledge extraction, right? But it still implies SNARK.
We don't know how to construct IVC without any knowledge assumptions. So I think the transformation from IVC to SNARKs does not require any knowledge assumption, but in order to construct IVC, and also in our construction, in the end, we will use the Fiat-Shamir heuristic, basically. We do require knowledge assumptions. So we don't get around this impossibility result. Does that help?
Yes.
Okay. So yeah, what are our contributions? Well, in this work, we introduced something called a split accumulation scheme. And we show that ZK NARKs with split accumulation schemes imply ZK IVC and PCD. And the important thing is that now we can actually construct this from a NARK, not a SNARK. So this is an argument which is not necessarily succinct. And we show that as long as this NARK has this thing called a split accumulation scheme, then this suffices for constructing IVC. So this is where the title of our paper comes from. And in theorem 2, we show that under the discrete logarithm assumption in the random oracle model, so here's our knowledge assumption, we're in this idealized model, the random oracle model, there is a NARK with a split accumulation scheme for R1CS, whose accumulation verifier is incredibly efficient. And this is kind of the size of the accumulation verifier is the main thing that we care about. Mainly, it has a constant number of scalar multiplications, constant number of field operations, and a constant number of random oracle calls. And to be precise, the number of group scalar multiplication, this is kind of the most expensive thing that we will need to implement, is, I think it's 3. So it has like 3 scalar multiplication, group scalar multiplication. So it's incredibly efficient in practice. And compared to prior work, this was logarithmic for all of the parameters above. Yeah. So I guess this also illuminates the question that Elaine was asking, that theorem 1 is in the standard model. So if we have a ZK NARK with a split accumulation scheme in the standard model, this implies IVC, period. And then I think IVC implies SNARKs also in the standard model. But in order to instantiate the ZK NARK, the only ZK NARK that we know is in the random oracle model. So we then need to make a non-black box transformation where we say, okay, we assume, now we have this construction in the random oracle model, and now we actually have to instantiate it with a real hash function and assume it exists in the standard model and that it is still secure in the standard model. So yeah, and we call these things split accumulation schemes, but they have nothing to do, they're not set accumulators. It's more that you can accumulate the verification of multiple NARKs. That's where the name comes from. Okay, any questions about the results? I mean, I guess I hope there's questions, but I'll explain how we get to them in the rest of the talk. Okay, so yeah, so how do we, I guess, to illuminate it one more time. So what is the pipeline? Well, we get IVC and PCD from, and we show it through theorem 1 that if we have a NARK and a split accumulation scheme for this NARK, this gives us IVC, and then here's the transformation to ZK NARK. But we don't know how to, instantiate this in the standard model. So this is exactly where this separation comes in. We have this split accumulation scheme in the random oracle model, and then we use a heuristic to say that we assume there exists one in the standard model. Okay, and the same thing holds for, we can, if all of the components are zero knowledge, then in the end we get a zero knowledge version of IVC and PCD. And I won't go into the details of zero knowledge IVC. For that, you'll have to look in the paper. But at a very high level, it means that the witnesses are remain hidden, the witnesses in the IVC computation. Okay. So we also implement.
Can I ask a question? So, like, what about this Gentry-Wicks law bound? Does that apply to the this IVC PCD?
Yeah, I mean, it really implies that what we're doing here, so that we are applying this heuristic step here, and this is sort of not surprising because of the Gentry-Wicks law bound, because it's the random oracle is a form of a knowledge assumption, and in order to prove our scheme secure, we need to be in, we can only prove it secure in the random oracle model. And actually we need to do something even stronger. We prove our accumulation scheme to be secure in the random oracle model. This is what we do here in the bottom. And then heuristically, we assume that if you instantiate this scheme, not with a random oracle, but a real hash function like SHA-256, that this gives you a split accumulation scheme that is secure in the standard model. But we can't prove that. This is a heuristic assumption, right? We prove it's secure in the random oracle model, and then we assume once you implement this with a real, hash function, this is still secure. Yeah, so this is, where we certainly make use of a knowledge assumption. So there's we don't circumvent any lower bounds. Okay. And yeah, so these are the theory contribution, and we also implemented things. So we implemented atomic and split accumulation as part of the ArcWorks ecosystem. So there's an Arc accumulation library, which is online now. And then we implement accumulation-based PCD as part of the Arc PCD library, which I don't think it's quite online yet. It might be. I have to check back on that. I certainly wasn't the core contributor on the implementations. This is Protrusion Will did a bulk of the work. But if you want to play around with this is actually available, implemented in high quality code in Rust. And it enables a straightforward comparison of the cost of PCD across different parameters. So all of the previous approaches, and we can see that for the most part, we compare favorably across, all of these things. And one key thing that is favorable is that you need to, so in order to implement these recursive proofs, you need to have a recursive circuit. So you prove that some verification procedure was correct. In order to do that, we use these cycles of elliptic curves. I might go into this a little bit at the end if we have more time. So you need to find two curves that are, cycles of each other. So the field of one curve is the same, the size of the field of one curve is the same as the order of the group of another elliptic curve. And in BCTV 14, you needed to have a pairing friendly cycle. So this needs to be not just a cycle, but both of these groups need to have pairing. So these were actually kind of difficult to find. So a large part of the contribution in BCTV 14 is efficiently finding an efficient cycle. And then in Halo, it removed the assumption, or it removed the need for a pairing. It now only required a group where the discrete logarithm is hard, but no additional structure, no additional bilinear map. But these curves need to be FFT friendly, which means really that the size of the field has a high two-adicity. because you need to compute FFTs efficiently. And in our work, this works on any cycle. There's no more requirement for FFTs, which has a lot of practical benefits and allows us to use more efficient curves. And we found that our approach has much lower recursive cost than BCTV 14. Okay, so now let's get into the weeds. So let's have a small background on recent advances in PCD. So a little bit more formally, we have here the definition of IVC, where we already discussed this. We have some computation f, or some function f, that is evaluated on z and w and output z prime. And the prover in IVC always takes as input the new z prime and pi prime. So that was the output of the previous prover. And completeness says that if the verifier accepts a proof and an input, then the verifier will also accept kind of the next step of the computation. So the prover applied to the previous input and the old proof. And proof of knowledge says that basically if an adversary produces z comma pi, then we can extract the complete transcript of the computation so far. So not just the witness for a single step of the computation, but we can actually extract many steps of the computation, or so all of the steps of the computation up to the root of the computation. And efficiency says that we have an efficiency requirement saying that the size of the proof doesn't grow. This is really, really important. Otherwise, constructing IVC you could just append proofs. So it would be fairly trivial. And yeah, so this is the definition of proof of IVC. I won't go into the zero knowledge details, but there's also an appropriate zero knowledge definition. So, and what we need to construct this is a ZK NARK, not a SNARK, with preprocessing. And so we construct a ZK NARK for a relation, and we have an indexer which takes as input. So our relation is formulated as a circuit. The circuit takes in an input x and a witness w, and the indexer preprocesses the circuit and outputs a proving key and a verification key, which depend on the circuit. And then the prover gets his input x and the witness, produces a proof, and the verifier only gets his input x and the witness and the proof, as well as the verification key. And yeah, what we need is that this is complete and that this is an adaptively secure proof of knowledge. And optionally, if it's a SNARK, then we also require that the size of the proof is much smaller than the size of the circuit. So constructing IVC from recursive composition of SNARKs, so this is the previous approach, just says that we have our function being evaluated. And what we then do is we create a circuit, or we create a relation which evaluates the function and runs the verifier itself. And then the prover creates a proof that the function was evaluated correctly and that the verifier would have accepted the SNARK. So yeah, so this R here is the important thing. This is, so the prover runs in his head both the function f, but also the verifier. So the prover needs to prove that the verifier would have accepted the proof. And the verifier at the end of the computation just gets in the start and the endpoint of the computation and the final proof and simply accepts it. And completeness follows from the SNARK completeness. Soundness basically recursively extracts the transcript using the SNARK knowledge soundness. And here you need to be very careful with the size of the extractor blowing up, as Elaine was saying earlier. And we need to have some strong knowledge properties on the SNARK. So we need to be kind of careful in how we do this. And yeah, the important is this does not work in the random oracle model because we make very non-black box use of the verifier. So the verifier cannot be a random oracle verifier. It actually needs to be, right, we actually need to put the verifier into a circuit. And yeah, and efficiency is the size of the SNARK of the proof for R, which, you know, ideally say we have a constant size SNARK, then the size of the proof is constant. And because we're proving a statement about the SNARK verifier, we need that the verifier is succinct, is efficient, in order such that proving the statement about the SNARK verifier doesn't grow. So, you know, we need to have basically yeah, it's important that basically we can fit the size of the verifier into the prover. And if we didn't have this, if we have the sublinearity property, then this will actually be possible to find a bound on R such that we can always fit the verifier in there. So you might wonder though, you know, is it really necessary to have this sublinear verification paradigm? And as I already said, that in more recent works, we were able to come up with a new primitive, an accumulation scheme, an atomic accumulation scheme that showed, okay, this isn't required anymore. So what is an accumulation scheme? So say we have a bunch of inputs to a predicate. So we have some predicate, you know, just any good old predicate. And we have these inputs Q1 through Qt to the predicate. And we want to wonder whether, you know, the predicate applied to each of these input, whether all of them are accepting. So, so if the phi applied to Qi for all I is equal to 1. And what the accumulation scheme does, it accumulates all of these predicate checks into a single accumulator. So the accumulator, we start with some basic accumulator, and then we have an accumulation prover that takes in the new predicate input and the old accumulator and produces a new accumulator. And it does so, and so it basically accumulates these checks into the accumulator, but the size of the accumulator doesn't grow, it stays constant size. And then we have a verifier, and the verifier, it doesn't have to check the predicate itself, but it just checks that this accumulation step was done correctly. So it just does a small check. And this is indicated, you know, why do we do this? Well, we do this for efficiency purposes. The verifier here is a much smaller box than the phi here. And this is on purpose because checking this one accumulation step is supposed to be really efficient, much more efficient than checking the predicate itself. And if we do this over and over again, then in the end, we have, you know, we know that all these accumulation steps are done correctly. And now we have this final accumulator, and this accumulator can go into a decider. This decider can be a little bit more expensive. We only need to run it once. And then the decider will say, okay, this accumulator looks valid or not. But the important thing is that if the decider accepts and all of the accumulation steps were done correctly, well, then this implies, maybe under computational assumptions, but this implies that all of the predicates would have accepted. So, right, there's two ways to check that phi of Qi is equal to 1 for all I. One is just checking it individually. And the new way of doing this that we propose or that we use is just accumulating all of the checks into a single big check that is done by a decider. And computationally, these two, or one implies the other. Is this clear? Okay, so and the cost, ideally, the cost of the verifier is smaller than the cost of the, so this process ideally saves you computation time, because running the verifier t times plus the decider once should be cheaper than t times running the predicate or evaluating the predicate. Okay, and it turns out that even from this notion of accumulation, we can construct IVC. So how does this work? Well, the idea is now that the accumulation prover does two things. It runs the IVC prover does two things. It runs this accumulation principle in his head. So accumulation for what? Well, we now have an accumulation for SNARK verification. So the predicate that we're accumulating is in fact the SNARK verifier. So we say, you know, right, because IVC, in essence, it checks a bunch of, what does IVC do? Well, it checks a bunch of SNARKs. You know, it's if I have T steps of computation, then the prover in his head needs to check T SNARKs. But what it can do is, instead of you know, checking these SNARKs themselves and constructing full-on, you know, proofs that they were that SNARK verification was done, is the idea is that we will accumulate these SNARK verifications using an accumulation scheme. So now I have in this orange box, I have an accumulation scheme for SNARK verification. And what I will do is I will now, as the SNARK prover, accumulate. I start with an accumulator, an IVC proof, and the input to my function, and I will accumulate the new proof. So this is the new predicate with the old accumulator into a new accumulator, and additionally I will evaluate the function, and then the accumulation verifier will simply say that you know, I will give you a proof that the accumulation verifier was evaluated correctly. So and this proof now becomes pi I plus 1, and then in the next step I basically just, you know, keep on doing the same thing over and over again. And the SNARK verifier now at the end, it checks the final decider. So it checks the final accumulator using the decider, and it also verifies the final SNARK. So what have we gained through this? You know, this seems to be, we've added a bunch of symbols and some colors. What have we gained from this? Well, the important thing is that now this recursive circuit, and this is really the costly part about, you know, doing this recursive circuit is really the costly part about IVC. Now it doesn't contain the SNARK verifier anymore. All it contains is the accumulation verifier. Am I frozen? No, okay. Yeah, all it does, it contains the accumulation verifier, which by assumption is much cheaper, right? Constructing an accumulation verifier is much simpler than, or it turns out having a SNARK with an efficient accumulation scheme is much easier, is easier than having a SNARK with efficient verification. So yeah, this is what we've gained. The green box is what we've gained. And soundness now relies on the same strong knowledge property of the SNARK, but only we now also need that the accumulation scheme is sound. And what we require now is that the accumulation verifier must be sublinear, but we don't actually require anymore that SNARK verification is sublinear, because never in this recursive circuit do we evaluate this blue V, the SNARK verifier. So, but the accumulation verifier must be sublinear. So this means that the accumulator must be sublinear and the proof itself must be sublinear. So we still need a SNARK. Yeah. Okay. So how do we innovate from this on, right? Like the final goal will be, we've already reduced the complexity of this recursive circuit by a lot, but we still have the sublinearity requirements on the proof and the accumulator. And in the next step, I'll show you how to get rid of those. Okay. But if there's any questions, please feel to jump in. But yeah, so the way that we get rid of it is using our new tool called split accumulation. So what does split accumulation mean? Well, it means that, say we don't have, say we now, what we want to do is we want to create an accumulation scheme for a relation. So what we'll do is not just for a predicate anymore, but, you know, a relation which takes as input an instance. So here written as QX, and a witness written as QW. And the all of these relations accept, or yeah, all of these. And what I want to show is that they exist witnesses. So the statement that I want to prove is that there exist witnesses, QWI, such that the relation for, yeah, that all of these relations are accepting, I guess. Well, that's not really how you say it, but yeah, and the important thing now is that the important thing to keep in mind, you know, visually we try to demonstrate this again, is that the instance, so QXI, might be short, but the witness itself could be long, you know. So in the end, this is going to be a proof. So what we'll do is we'll split our proof into a short part, the QX part, and a long part, the QW part. And now what we'll do is we'll have an accumulator. And again, this might be a larger accumulator. And the accumulator takes as input QX, and you know, we have a similar accumulation scheme. But now the key difference is that again, the accumulator can also be split into an accumulator instance and an accumulator witness. And now the accumulation verifier takes as input, it gets from the prover the accumulation, it doesn't have to read the entire accumulator. It only has to read the accumulator instance, and it has to read the input instance, and it might get an additional proof supplied by the prover. And we have a similar property that if all of these accumulation verifiers accept, and the final decider, so the decider will read the entire accumulator. So if all of these things accept, then we know that this is at least computationally equivalent to checking the relation on all of these inputs. So the important thing here now is that the verifier now has to read very little. It only has to read, you know, we can split our accumulation scheme into inputs and witnesses, and the verifier only really has to read these to instances and witnesses, and the verifier only has to read these instances. And yeah, so yeah, I'll talk about the security property in a second. But yeah, so this is the difference between split accumulation and normal accumulation. But it turns out that even from split accumulation, that even this weaker primitive, so this is a clearly, you know, clearly any normal accumulation scheme is also a split accumulation scheme, right? It would just be that the black box and the orange box are the same, and the black box and the blue box are the same. So the witnesses would just be empty. So any normal accumulation scheme is a split accumulation scheme. So the split accumulation scheme is a weaker notion, but it turns out that even this weaker notion is still suffices in order to construct IVC. So how does that work? Well, what we do is now we have our NARK, and the NARK might have a long proof, but we can split this proof into two parts, into pi x and pi w. And then the IVC prover gets its input. So the IVC proof now consists of the NARK proof, which again, it might be long, but it can be split into a short and a long part, and the accumulator, which again also can be split into a short and a long part. And now the IVC prover gets as input the entire proof and the entire accumulator, and then feeds to the accumulation verifier, or runs the IVC prover runs the NARK prover in its head for a relationship which contains the function and the accumulation verifier. But the accumulation verifier only needs to read the short parts. It only needs to read the short part of the proof and the short part of the accumulator, and then it can output a new proof. So this is, you know, I'll stop in a second and you can ask questions, but here the key insight here is that the accumulation verifier doesn't even need to read the entire proof. So this is how we're able to construct, and the recursive circuit now is really, really small. It is just this accumulation verifier, which just reads a short part of the proof and the function itself. And this is the size of the recursive circuit, which in the end will be the main thing to get efficiency, is now really reduced to kind of the smallest possible thing. And yeah, so soundness of the scheme relies on, again, we need the strong knowledge property for a NARK, but we also need now a strong knowledge property for the accumulation scheme. So we need that from the accumulation verifier, we can actually, or from the accumulation prover, we can actually extract the accumulation witnesses along the way. And the important thing is that the efficiency of this entire scheme is now, it depends on R. So it is independent of the size of pi w and AW, and only depends on pi x and AX. Okay. Sorry. So are there, I know this was a lot, but we'll see this very concretely on an example, and maybe then things are a little bit more clear. But if there's any questions.
Yeah, I actually have a couple of small questions. So how do you guys treat the base case? So what would pi 0 and A0 be?
Yeah, you can come up with like, this is a very good question. I think concretely, there's kind of, our accumulators just kind of have, there's a null accumulator, kind of that, if you accumulate, anything to it, then yeah, there's basically a base case for the accumulator and the proof. So yeah.
I see, and then I assume the NARK itself like sort of keeps this in mind, like what a null accumulator is, and just accepts it.
So that's one way to do this, or to kind of to split it off. I think in our concrete scheme, I think there's an accumulator for kind of a trivial statement that always accepts, but I'll have to look into, like, you can, in the end, it's a couple group elements. I think if you literally just set them to be the identity elements, then I think, this just works. But
okay,
I would have to think about the details of like, in our concrete scheme, how it works.
Sure, for sure.
But it's a very good question. Yeah.
Yeah. So the other question I had is, what's considered the public IO of the NARK right there? So like, which of these inputs are like the witnesses as thrown in as input, and which of these are like sort of, the public IO?
Very good question. So the public IO are basically all of the things that the verifier reads. So this is the short part. So pi x, ax, I, and zi. So everything that the verifier reads, or that goes into here, this part, that's the public inputs, or those are the public inputs, and those are the public outputs. And then AWI and pi wi. And I didn't demonstrate this here, but there might be an additional witness, to evaluate F. Those are all the witnesses.
Okay, so just that additional like non-deterministic input to F is considered the witness.
Yeah, F might have a non-deterministic input as well. That would also be part of the witness. But this is a key insight, is that I can even split I can basically put part of the old proof. One way to say this is that I can put part of the old proof into the witness instead of having it be part of the IO. In all previous IO, in all previous IVC construction, the old proof was part of the IO. In this construction, we can make part of the proof be just to be a witness.
I see.
That's that's just one very simple way to think about what we're doing here. Is we're splitting up the old proof into part IO and part witness.
Okay, cool.
But obviously this doesn't work for all proofs. This is like a very special Yeah.
Mm.
Okay, cool. Any more questions? Okay. I'll skip over this. You know, this is, I guess, yeah. Here, our main theorem that we can construct IVC from where the only sublinearity requirement is really that the accumulation verifier must be sublinear. The proof does not need to be. So I'm running a little bit out of time, I guess. How I'll try to give a quick overview of the construction, or what's the, what are the time constraints? Okay, if I go 10 minutes over, 5 minutes over?
Yeah, sure. Just go ahead.
Okay, I'll try to keep things brief. So what we do is we construct an accumulation scheme, or a NARK and an accumulation scheme for R1CS. And one of the nice things is that this is really, you know, it's really a trivial kind of scheme almost, but through our pipeline, it is powerful enough to give you the entire power of IVC and PCD, which is kind of amazing. So what we do is we construct a proof for R1CS. So R1CS is a formulation of NP. And it is nice because it is very structured, but also very simple. It's very closely related to arithmetic circuits. And the way that it works is that I have some matrices, some public matrices A, B, and C. And I have a vector X, that's the IO, or the public input, over a field. So all of this is done over some field. And the proof is that if I, that there exists a secret vector W, such that for Z, which is the concatenation of X and W, AZ Hadamard product with BZ equals CZ. So this is the check. So this is the element-wise product. And I said there's a very simple transformation, very direct transformation from arithmetic circuits to this. And this is widely used in proof systems today because it gives you a nice balance between structure and expressivity. And X is very important, but you know, we'll for the rest of the talk, for simplicity, we'll just ignore it. So what is the simplest non-interactive proof of knowledge for R1CS? Or what is a trivial R1 proof for R1CS? So say, you know, I have A, B, and some public input X, or A, B, and C, and I want to prove to you that this is a valid R1CS instance. How do I do that? Can one of you tell me? Like, doesn't have to be succinct, doesn't have to be zero knowledge, just
yeah. You could just send Z over, right?
Yeah, you just send Z over, right? You send Z over. You literally just send the witness. You know, I mean, this is a trivial proof system for any NP language. Is you just send the witness. We'll actually do, and then you know the verification just checks the thing. And this is almost the NARK. So this is a non-interactive proof of knowledge, or a NARK is for R1CS, and we'll use almost the same thing. We'll just add some commitments to it, and in particular, we'll commit to these vectors AZ, BZ, and CZ using a homomorphic commitment. So you can, like the Patterson vector commitment, for example. So that's the entire proof system. And why do we send these commitments? Well, they will allow us to accumulate proofs. So now this is the NARK. This is it. And now what we'll do is we'll build an accumulation scheme for this NARK. And then we will show that basically once this accumulation scheme exists, well, then through our entire pipeline, we'll get IVC. Okay. So what does this accumulation scheme look like? So let me move things around. So this is a first attempt. So I have, you know, I have my proof, which is the vector Z, and these commitments to AZ, BZ, and CZ. And I now can split this off into a short part, which is just these commitments. So these are 3 group elements, and a long part of the proof. So here you can already see the splitting. So Z is long, right? Z is an entire vector. It's the same size as the witness. So this will become, it's an Fn. So this will be my pi W. So I've split this off, and let's assume I have an accumulator, and the accumulator kind of has the same form. So it's AX, 3 commitments, and AW, a vector. And now what I want to do, so what is this accumulation scheme? Well, I want to combine checking these things into basically, instead of having to check these 2 things, I want to combine them into a single thing. So into a single check that, into a single, say, new accumulator. So the simplest idea is I just take, that the first idea that we had is, well, what if you just take basically a random linear combination of it? So, you just sample some challenge beta, and to make this non-interactive, or the verifier could send the challenge beta. It's we can write this as a Sigma protocol and then compile it into a non-interactive protocol using the Fiat-Shamir transform. And so what we'll try to do is, let's just see what happens if we just combine everything using our challenge beta. So the first thing that we'll combine is our witnesses. So we combine AW plus beta times pi W. And the commitments will also, combine. So we'll have, we'll write CM prime is equal to CM prime plus beta times CM. And this will be our new accumulator instance, will be these new commitments, just linear combination. Recall that everything is homomorphic, and the new witness will be the linear combination as well. And the verifier needs to send the challenge, but we can later make this non-interactive. And the prover then would just send the the new accumulator instance, and the verifier would check that accumulate the commitments herself, and check that CA prime plus beta CA is equal to CA prime prime for all 3 of them. And now the decider, basically, so this is now let's see basically, what does the decider still accept this new thing? Well, so the decider would compute, or let's just y prime be the witness of the accumulator. Okay, so this is this new vector. And then it would check that CM prime prime is equal to commit of M times Y prime. So M, this is, again, you have to replace M with A, B, and C. So it does 3 checks here. And it turns out this is true, right? So if you expand this first check, this actually works, right? We have A times, let's just do it for A times Y prime is, if you look here, is A times AW plus beta times pi W, and just through the linearity of it, it exactly works out. You can see this in this green color here. So everything nicely works out. And then the third check is this R1CS check. We have to do this R1CS check where AY prime times BY prime is equal to CY prime. And it turns out this doesn't quite work, okay? So if you expand this, you get some, you get an AY times BY term. So this is exactly this should be equal to CY, and we get plus beta squared times AZ times BZ. So this is equal to CZ plus beta times some cross terms. But this isn't quite the same as C times Y prime, which is CY, which was just the linear combination between CY and CZ. So cy plus beta cz. So we're almost there, right? We have cy plus beta squared cz plus beta times junk is what we get, but what we really would want is cy plus beta cz. It turns out that, you know, we can basically with a little bit more work, and yeah, I don't know if I want to, okay, I'll try to go through this. You know, actually, to be honest, I'll skip over this. With a little bit more work, and basically we just have to add one additional element to the accumulator, which accumulates this Hadamard product. We can, you know, we can make this work, and yeah, we kind of have one additional proof element where we commit to the junk terms. You know, we commit to them in the first step, then we get the challenge, and then yeah, then it nicely works out. And the important thing to see is that the verifier, you know, is even this final accumulation verifier, it does really little work. You know, it checks that the linear combination between basically a couple commitments, and you know, also for this Hadamard check, it does, and that's the entire work that the accumulation verifier does, and this is all we need to implement. So if you counted, I think if you counted this, it would be 5 group scalar multiplications. It turns out that through some tricks, you can actually get this down to 3 scalar multiplications. And there's already some follow-up work that, you know, has a slightly different split accumulation scheme for exactly the same protocol. I think it's called Nova is the follow-up work, and they do it with 2 scalar multiplications. So, you know, it's really, although they you know, their scheme only works for IVC, but and has some other issues, but in general, you know, it turns out you can do this insanely efficiently. So this accumulation verifier is really, really efficient. And to kind of bring this back to the high level, even though, you know, we basically all we do is a simple Sigma protocol here through our pipeline, you know, this gives us IVC or PCD. Yeah, that's it, sort of. So, and the cool thing is, you know, there's no PCPs, no linear PCPs, no IOPs, and so on and so forth, no FFTs inside. And, you know, you could even, you know, if you follow the pipeline all the way, you can even get a SNARK construction from this. The major caveat is the non-black box use of the random oracle. And, you know, one interesting question, of course, is could we replace the use of this random oracle? And I'll show you, we implemented all of this. You know, this is great work mainly by Pratyush and Will. So the blue things are, the blue and orange things are the things that we newly implemented in this work. And I just want to show you the graph of, you know, this is the, wait, which one is which? So yeah, this is Gross 16 is the gray line. BCMS is the prior work that, you know, was based on Halo using atomic accumulation schemes. Why was this interesting, by the way? I didn't really point this out, is that BCMS has no trusted setup. Other than you know, Gross 16, if you use the prior constructions, you had to rely on a trusted setup. And our work also doesn't rely on, you know, trusted setup and all of this. And you know, the number of constraints are, I think it's a factor of 5 smaller, at least, or even more. And you know, I think there's still a lot of room for, like, I think the gap difference is correct. But I think there's still a lot of room for optimizations and you know, making the circuit even smaller. And yeah, this is measuring the number of constraints to accumulate one old accumulator and one new NARK. And this is really, you know, this is really what people care about, because the more constraints you have, the more expensive your prover is, the heavier hardware, you know, the more complicated this is to run. And you know, this directly translates into prover runtime, which people care about. Okay. Yeah. And oh yeah, I think this was a general case, and the IBC specific accumulator might be even lower. So yeah, thank you very much. You can find the paper online. It will also be at Crypto this summer. And yeah, let me know if you have any questions. Okay.
So if there are no more questions, let's thank Benedikt again. Let me start recording.